gusto, tengo el agrado de presentar a Manuel Lladser. Manuel Lladser es ingeniero matemático de la Universidad de Chile, se dedica a las probabilidades, actualmente es profesor titular en la Universidad de Colorado, en el Departamento de Matemática Aplicada, y su investigación dentro de las probabilidades se centra en colaborar con cálculos computacionales en biología. Y hoy día nos va a presentar su trabajo que se llama Non-asymptotic approximation in computational biology vía maximal coupling. Gracias, Juan.
Gracias. Bueno, gracias a Javiera y a Rodrigo por organizar la visita. Me dijeron que hablara en inglés y eso es lo que planeo. Si hablo en castellano me va a demorar 2 horas en la presentación. Así que voy a cambiar a inglés. Y, well, although I will be talking about computational biology, the main object here is a functional of a Markov chain. So if you work with Markov chains, if you have a linear functional of it, then this talk should also be interesting to you. So, all right, so let me give you the problem setting and statement. So we are going to be working on a Polish state space, capital S. A Polish state space is a metric space that is complete, and the main technical reason to work there is because a Markov chain is uniquely defined by its initial distribution and probability transition kernel, which we'll denote as P, when you work on a Polish state space. And we're going to use this notation: X follows a Markov mu comma P to denote I have a Markov chain with initial distribution mu and probability transition kernel P. Now, when necessary, although I will not assume this very often, we are going to denote the stationary distribution of the Markov chain as little pi. And here comes the main object of study here. Oh, sorry, one thing. Since I know that a lot of people with different backgrounds here, one can imagine that S is finite. This is a special type of Polish state space. In this case, the initial distribution is just a row probability vector of probabilities, and the kernel can be thought as a matrix. Okay, so if you don't feel comfy with the general metric space thing here, then think in terms of finite state spaces. And all the examples I will give are going to be finite state spaces, but finite state spaces that are sufficiently large to find this problem particularly interesting. So this is the main object of study, this random variable f sub n, that it's a linear functional of the Markov chain X, but that you're paying at time t a total value that depends on the time t and the state x sub t, and we are denoting that by the function little f. And a special type of additive functional is when this function f doesn't depend on time, and when the function f only corresponds to the indicator function of a special set t. So in this case, once you fix the set t, you are talking about the sojourn time of t, which is the number of visits that you make to that set in the first n transition. So that's the most classical example of an additive functional. And the problem that I want to address is the following. I want to approximate the distribution of the functional S sub n in something that could be called an intermediate regime. What is the intermediate regime? Is n is too large for exact calculations, meaning you cannot accomplish the calculation in any reasonable amount of time because n is too large. But on the other hand, n is too small to rely on the normal or Poisson approximations, which are asymptotic approximations, and hence the title non-asymptotic approximations. Okay. Now, at the end of the talk, I will give you an example that this regime fits perfectly well, and you will see that sometimes it's difficult to say, oh, I'm stationary, or you may not really believe your normal approximation. All right, so how do we address this problem, or what is the motivation for this problem? Well, in computational biology, there is this experiment called SELEX, where you produce on a pool of random molecules that have a certain function that you screen for. Okay? And for instance, these 12 structures, 12 RNA structures, catalyze the same reaction. And as you can see, the structures look very different. And now if this reaction has a medical application, you would like to construct molecules like this, kind of at random. Okay? And the question is how to do it. Well, to do that, you are going to produce random molecules, and you would like to determine the probability that you generate this specific structure in your random pool of RNAs. So I just said probability, so the question is how to compute the probability of observing a specific structure. So, yes? Yes. The RNAs are considered random, meaning you are assembling them totally at random. Many of them don't do anything, meaning they are not related to your reaction. Some of them are related to your reaction. Okay. All right, so here is an example. So this could be an RNA, and I will maybe be interested in this particular structure. Now, the structure has a physical structure. So it has a, in this case, a two-dimensional shape, but it also has certain RNA bases that must be fixed. This has to be an A, this has to be a base C, but also has some bases that are non-fixed. For instance, this N, doesn't matter what it is as long as it's complementary to that N. And in RNA, G is complementary to C, and A is complementary to U, meaning they can form a hydrogen bond that will give structure to the noodle that is the RNA that one is producing. So in this case, one is interested in determining the probability of seeing this structure, and one can model that mathematically as the probability of seeing a pattern like this, where 1, 2, 3, 4, and 5 are arbitrary bases, 5 prime, 4 prime, etc. are bases that can form bonds with the respective bases, like these ones. And then there are some fixed bases that for some reason you observe that in your experiments they seem to stay constant. This base is always a G, this base is always a C, etc. So the question is, what's the probability that a random RNA in a select experiment adopts this secondary structure? That's the mathematical question. And to answer that question, one can do it easily using conditional probabilities. And the answer would be, well, first, if you want to adopt that structure, you must first contain this motif. Okay? And what I mean is that no matter what the RNA is, somewhere it has to contain the motif. The motif is a fancy way to say the pattern, the specific pattern of interest. Okay? But even though an RNA may contain that motif, it may not necessarily fold in this particular way. Okay? So maybe this contains a motif and it falls in a way that is totally different from what you are interested in. Okay? So then you multiply that probability by the probability of adopting the shape given that you contain the motif. All right? And that's the probability of observing that specific structure on the random RNA pool. Now, the second probability, the conditional probability here, it's usually computed using biophysical arguments. People usually use Monte Carlo arguments. And it's not something that I am particularly interested in because I don't consider that very mathematical. But the probability of containing the motif is something that is mathematical enough to say, oh, I would like to compute that probability. Okay? Now, what is challenging is that usually the probability of containing the motif is very small because the motifs are very long, which makes it a very improbable pattern. Okay? So if you try to approximate the probability of containing the motif via Monte Carlo simulation, you will conclude on a reasonable amount of time that that probability is 0. You will not be able to see that motif at all on your simulations. So that's why this is an interesting term to pay attention mathematically. So we want to compute that probability, and if we cannot compute it, we want to approximate it. Okay? Is it so far clear, the motivation and what I'm trying to do? Okay. All right, so instead of focusing on this complicated motif, and there are ways that we know how to turn this complicated motif into simpler motifs and combining all those motifs questions together, let's look at something that everybody can relate to. And here's a toy problem. So how many times will AB occur in a random binary text. So you are going to generate A and B is totally random, and you want to say, how many times will I see the pattern AB? Okay? It's not a biological motivation, but it's kind of the same question, just on a random text. Okay, so here's the general strategy that people have done on the literature to address this type of questions. Well, first, using recursions or operators, people can do exact calculations as long as your text is not sufficiently long. Okay? Now, if the motif itself is frequent, meaning the probability of observing the motif is not too small, then you will get a normal approximation. All right? Because the number of times the motif is roughly the sum of several random variables. They are not really totally independent, but there is confined dependence, so you will have a central limit theorem, and you will be able to get a normal approximation. But for long motifs, the motifs themselves are usually very rare, super rare, and then the normal approximation is not going to be a good approximation, so people use the Poisson, and sometimes when the motif can self-overlap, they use the compound Poisson approximations. Okay? So the way in which the motif can overlap with itself defines the clamp distribution, and the clamp distribution now is used to determine approximately the probability of seeing that motif at least once. But all these cases are either exact but short text, or asymptotics, and either long text or stationary text. And usually for keeping track of complicated motifs, you are not going to work with really long text. You are going to work with rare motifs, but usually the method we use to keep track of the motif, to say that the Markov chain you're working with is stationary, is usually a very bad assumption. Okay? So you are kind of typically on a situation that is not addressed by any of these three settings. So the question, what about intermediate size text? What do we do then? All right, so I will show you what do we do then, and I will tell you a bit of the story. And first we're going to see how we will compute the probability of observing AB 17 times in a random text of length 100. How will you do that calculation exactly? All right, so here is what you will do. You will construct a automaton like this one. This one happens to have 3 states. The initial state is pointed by this arrow without labels. And the idea is that if somebody gives you a text, like this text, starting at this so-called initial state, you're going to read the text and then start following the arrows based on their labels. Okay? So if you start at 1 and you read an A, you move to state 2. So you start at 1, you read an A, you move to state 2. If you read another A, you stay at state 2. You stay at state 2. Now you read a B, you move to state 3. And this automaton has the following property. Every time that you hit state 3, you just completed one match with AB. All right? So I hit state 3, I just saw AB. I hit state 3, I just saw AB again. I hit state 3, I just saw AB again. All right? Is it clear? Now, this type of automaton can be constructed for very complicated motifs, much more complicated than AB. But the idea is that the more complicated the motif, the more complicated the automaton itself. The number of states will start to grow very fast for not so complex motifs. Okay? So imagine that you have an automaton that has thousands of states, and now you want to ask, what's the probability that I visit that 0 times or 20 times for whatever reason in your motivation? All right, so well, how many times will AB occur in a random binary text? After I construct the automaton, the answer is the sojourn time of state 3 in this particular case. So if you visit state 3 20 times, it's because you saw AB 20 times in your text. Okay? And now what we want is to let the length of the random text to be fixed, because that's the length of the random RNA. And now we would like to consider among all possible random RNAs, what's the probability that I see AB a certain number of times. All right? So we are again down to a sojourn time, which is again a special type of a linear functional. All right, so let's see how to do that. So here comes something that people that have taken basic probability should understand. So there are many models of random text. It may have memory, it may not have memory. To make things simple, let's suppose that text has no memory. It's just a random sequence of A and B's. Suppose A happens 40% of the time, B happens 60% of the time, and there is no correlation between different pieces in the text. Now, you can address more complex models, but let's stay exactly on this simple setting. Okay, so then when you read a random text, this automaton, which is deterministic, becomes a Markov chain on 3 states. Okay? Why? Because when you are at 2, well, 40% of the time you will read A, so 40% of the time you will stay at 2. And 60% of the time when you are at 2, you will read a B. That is to say, 60% of the time you will jump from 2 to 3. Okay? So the text model transformed the automaton into a Markov chain, and now I erase the labels. Originally we had letter labels, now we have weights on the edges that tells us the probability of crossing that edge from each specific state. All right? Okay, so now we have a Markov chain. And I would like to know how many times I will visit state 3, which is the one keeping track of AB. All right, so here's your probability transition matrix, P. All right. Now, why do we like the probability transition matrix? Well, we like it because we can keep track of visits to state 3, keeping track of how many times you cross that edge. Do you agree? Every time you cross the edge from 2 to 3, which is the only way to hit 3, means you made a match with your pattern of interest, in this case, AB. Now, to do that, we are going to make up something. We're going to make up a dummy variable z, little z, and we're going to multiply the column associated to state 3 by that dummy variable. And because there's only one edge hitting 3, that means that this is the only non-zero weight on the last column of P. Now, why are we doing that? So, for the following reason. If I forget about C, meaning I assume that C equals 1, and I take the 10th power of P, then you will see in row 1 and column 1, 36%. So, you know from basic probability that starting at state 1, there is a 36% chance that after 10 transitions, you will be back at 1. Everybody? However, that's when I put C equals 1. What happens when I let C to be an arbitrary variable? Well, when I let C to be an arbitrary variable, that 36% gets split into several coefficients of a polynomial. And the question is, what do those coefficients tell us? Well, this coefficient, the coefficient of C to the 0, has no C. The only way it can have no C is if I never cross that edge. Do you agree? But this coefficient of C to the 4 appears because I must have crossed that edge 4 times exactly in 10 transitions. Yes or no? So, if you add up these coefficients, you go back to 36%, but because you included the dummy variable Z, now you have a polynomial in Z. And if we focus on the coefficient of C squared, what we are saying is the following, that knowing that you started at state 1, there is an 18% chance that you end at state 1 having visited state 3 only 2 times. Okay? So this gives you an algebraic way to keep track of the number of times you visit a specific set of states just by considering powers of this matrix P sub Z. Okay? All right, so if we want to formalize what we just did, this is what we just did. The moment generating function of the number of visits to state 3 in 10 transitions, which I'm calling T sub 10, the moment generating function, which by definition is this polynomial or Taylor series, if you want to call it, can be computed by computing the 10th power of PZ, the initial distribution, and because I don't care about where the Markov chain ends, we're going to multiply by a vector of 1s. Okay? So that's a theoretical formula for the moment generating function after 10 steps. And of course, you can do this after 100 steps, after a few thousand steps, the formula still applies. So if T sub 1,000 is the number of visits to state 3 in 1,000 transitions, then the moment generating function of that random variable can be computed in that way. Yes?
After that many transitions, I mean, not even have gone back to it. I mean, had visited 3 many times, but didn't go back to state 2. There's an error from future too, so I could be just running around 23.
Yes, but the whole idea is that this is keeping track of all paths of length 10 that start with initial state mu, which in this case will put all the mass at state 1. Okay, so this will be 1, 0, 0 as a vector. And then you're saying, I don't care where I end. You may care where you end, but I'm in this question, I don't force to not end with AB. I could also ask that question. I could say, what's the probability that I see AB 3 times, but I do not end with AB? Okay? In that case, this wouldn't be a vector of ones. I will put mass, I want to end at 1 or at 2, but I don't want to end at 3. Better? Okay. Now, the point of the toy example is to show you that the longer the text, 1,000 transitions means I have an RNA of 1,000 bases. The longer the text, the higher the power of the matrix P sub C that I need to consider. Okay? And the power 1,000 of P is probably going to be the stationary distribution for this small chain, but for a large chain, it's not clear that you're going to be too close yet to your stationary distribution. Not only that, if you really want to know the number of visits to state 3, here you're taking the 1,000 power of a polynomial matrix, and that's going to be expensive to compute. Now, I want to make a warning. That's based on questions people have asked me after I given this talk. You don't compute P sub C to 1,000 multiplying P sub C 1,000 times. You don't do it that way. What you do, you compute the square, the square, the square, the square, until you get sufficiently close, and then you multiply by a small power of P sub Z. Okay? However, that operation is also very expensive, because every time that you take a square, you're taking a square of a polynomial matrix with higher and higher and higher degree polynomials. So even though you start very fast taking the squares, rapidly you start to slow down on the computation. Okay? Yes? What's the form of P sub Z? You insert a factor of Z in any column associated to the set T you are interested to visit.
Okay, so you just multiply each element by Z.
Yes. Okay. Each column in the set T that you're interested in this case was column 3, because 3 marks AB. Okay. Good? All right. So the question is, can one avoid this large power? Can I avoid taking the 1,000 power of the matrix? Can I do something much simpler? And what I would try to convince you is the following. Yes, roughly a 12th power will suffice. Meaning, to get a good approximation of the distribution of T 1,000, you don't need to worry more than a 12th power. And of course, you prefer a 12th power rather than the 1,000 power, regardless of how you end up computing the 12 or the 1,000 power. Okay? So, and the question is, how am I going to make that happen? Okay? Why I can reduce the complexity so much? All right, so let's see how we end up with that 12th power over there. All right, so before we do that, I want to give you an intermezzo of perfect simulation, because the idea we're going to use was used earlier to simulate Markov chains, stationary distributions perfectly. Okay? But I want you to keep something in mind. The stationary distribution of a Markov chain is an asymptotic object. You converge to it if you don't start stationary, but it's something that you observe in principle at infinity. And now I want to change the question. I don't want to observe something at infinity. I want to observe something that has evolved from time 0 to time n, where n is perhaps far enough to not have a stationarity yet. Okay? So I want you to keep that in mind. All right, so here comes something that is due to the Markov chain literature. It's called a minorization condition. And what says the minorization condition? And this works on any Polish state space. Says suppose that there is an integer k greater or equal than 1, a real number alpha, and a probability measure e, such that the kth power of the matrix P is bounded from below by alpha times e. Now, when you look at that, you may say, what does that mean? Because here I have a matrix, and here I have a probability vector. Or I have an operator, and here I have a measure. Okay, so I'm comparing apples with oranges. Well, the idea is that you are comparing every row of p to the k with this probability vector, and you want pointwise inequality. Make sense? So p to the k greater or equal than alpha e means that I want every row of p to the k bounded by below by alpha times e. Okay? All right. Well, if this is possible, if you figure out a k, an alpha, and an e that does this trick, these beautiful things happen. One can simulate the stationary distribution pi, assuming that it exists, without pre-computing it. Meaning you can simulate perfectly from the stationary distribution without ever analytically solving for the stationary distribution. All right? Now, if you're interested in this, I'm giving you here a lot of references for it, but I will give you my explanation, which I like very much because when I saw that explanation, I believe this as, oh, this is cool. I believe it now. Okay? So here's my explanation. Because p to the k is greater or equal than alpha e, you can write p to the k as alpha e plus 1 minus alpha m, and you say, what is m? Well, you solve for m. M has to be this. Okay? But m, which is p to the k minus alpha e over 1 minus alpha, has no negative entries because p to the k is above alpha e. Okay? But the rows of p to the k add up to 1. The rows of alpha e add up to alpha. So all the rows here add up to 1 minus alpha. So when you divide by 1 minus alpha, you get now a probability transition matrix. Okay? Now, in the Markov chain literature, the matrix M is called the residual chain. Okay? So they talk about the residual change. They refer to that operator or transition matrix M. Now, because you can think of E both as a measure or as a Markov chain, I mean, an ID sequence is also a Markov chain. Do you agree? An ID sequence is also a Markov chain, but from the point of view of operators, it's a Markov chain where the matrix is constant. All rows are identical because there is no memory of your current state. The next state doesn't know who you are to be produced. Okay? So, because of that, if you take the nth power of p to the k, you will get that even though you should have 2 to the n terms, you can simplify a lot to get an expression like this. But now if you let n tends to infinity, because alpha is positive, this term disappears, and then you get that this p to the k n will converge to pi, and then this will converge to this series. A series where you have a geometric distribution where the value that the geometric distribution takes, which is I, is the same as the exponent used by the matrix M. Okay? So what does that mean? It means that to simulate pi is enough that I simulate a geometric distribution with success probability alpha. Suppose alpha is 17. And then what I do, I start with initial distribution E, which is this minorizing measure, and evolve the Markov chain M 17 steps. Okay? And that's the big secret. Okay? That's how people can say that, I can simulate perfectly from the stationary distribution without pre-computing it. Because it's very easy to write a quadratic algorithm to find what alpha is and what E is. It's very simple. And then once you know alpha and E, you know what M is, and now you know how to simulate this chain. Okay? All right. So summarizing that algebraic expression, we have the following. If p to the k is greater or equal than alpha E, and t is a geometric alpha, and y is a Markov EM, then y stop at that time t has distribution pi. So if you stop this residual chain at a geometric time, you will have distribution pi. And that's the basics to do perfect simulation. Okay. All right, so here comes another thing. This is to simulate pi exactly. What if I want to simulate pi approximately? Well, you can show that if you force t to be small, say less than c over alpha, the stop process has a total variation distance from the stationary distribution that is at most e to the minus c. Okay? So if you force the geometric to take a small value, at most c over alpha, the error between the stationary distribution and the stop process is going to be at most e to the minus c. So with a sufficiently large c, this is going to be very small, and hence you are going to get an approximate simulation of pi, approximating total variation distance. Okay. So in words, truncated versions of t lead to approximations of pi. So that being said, I want to now go back to my original question. My question was not about simulating pi, it was about approximating a functional of the whole chain. So question, can one adjust the above argument to approximate instead the distribution of an additive functional of the chain? So that's the question I'm asking. Can I adjust this now to approximate the distribution of the history of the process rather than the asymptotic object that is pi? Right, so let's see how to do that. The answer is, of course, yes, or I wouldn't be giving the presentation. So here comes the trick. The trick in this specific example. Well, here's your matrix P, and observe that every row here is bounded below by the vector 0.40. 0.40. Do you agree? So there is a minorization condition with alpha 0.4 and the vector E010. Okay? So using the residual matrix, I can say that P is 40% E and 60% M for the residual matrix M. Now, what does that mean? It means that to simulate the change, you can do the following. 40% of the time, you transition according to E. In this specific example, 40% of the time, you go straight to state 2. But when you go straight to state 2, you don't care where you came from. But 60% of the time, you use the residual chain M, which may have memory in it. Okay? So 40% of the time, you jump to 2. 60% of the time, you jump depending on where you are. So I'm thinking of a process with memory as a mixture of a process without memory and a process with memory now. Why is that useful? Well, we wanted to know how many times will I visit state 3 in 1,000 transitions, and if you want to go brute force, you will need to compute this polynomial. Can one avoid that large power? Yes, because P being a mixture of a memoryless process and a process that actually is not memoryless, the 12th power of MC will suffice. Okay, so you say, well, why the 12th power of MC? So let me explain why. It will suffice for a decent approximation, not for the exact answer. Exact is too expensive, so you usually go for an approximation. Okay, so here's the situation. Well, we said P is 40% of the time E, 60% of the time M. That means that 2 every 5 transitions are controlled by E. Do you agree? 2 every time transitions, the chain will break the memory. Because E doesn't know, all the rows of E are identical, so you're breaking the memory. So here is a typical realization of this. M, 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 E, M, M, E. That's a typical realization. Okay? Now suppose I ask you, how many times did I visit state 3? Well, I can say how many times the first 4 transitions visit state 3, and how many times these other transitions visit state 3. But what is happening is that the number of visits to state 3 here and the number of visits to state 3 there are independent now. are independent because E broke the memory of the chain. Do you agree? So it's like this process with memory, now you're cutting it at random pieces and say, this piece has no memory about this piece, neither about that piece. Okay? Okay, so now I need to worry about adding independent random variables. But why I prefer to add independent random variables? Because to compute the number of visits to state 3 in the first piece, I only need to compute MC cube. I don't need to compute MC 1000. MC cube. And to compute the number of visits to state 3, I need to compute MC squared now. All right? So rather than taking PC to 1000, I'm taking MC to small powers now. All right? So that's what I'm doing. So if you look at your favorite textbook in probability, there's this whole theory about run lengths when you flip a coin. Okay? A coin that is heads with probability alpha, tails with probability 1 minus alpha. Here the coin has two sides, a side that is called E and a side that is called M. E happens 40% of the time and M has 60% of the time. So now, if you see the literature and you say, well, what's the longest run of M's in 1000 transitions? That corresponds to the largest power of MC you will need to take. And that is the log in base 1 over 1 minus alpha, or of alpha n, which happens to be 11.7, which is approximately 12. Which means that to compute approximately the sojourn time distribution in 1000 steps, I shouldn't have to worry of powers much more larger than 12. Okay. And what is good about this is that the scale is logarithmic in n. So you transform a problem of size n to a problem of size roughly log of n. So to appreciate, if n is a million, you transform the millionth power problem into something of log of a million, let's say 6. A millionth scale to a 6 scale. So you bring things that are unachievable exactly to the realm of things that are achievable now, because you reduce the power of the problem a lot. All right, so hopefully you appreciate the punchline, the reduction of the problem. Now let's see the math, and now comes the whole thing about all the mathematical results, but to me the punchline is the end of the talk, okay? I mean, when you see that, you know this is the paper someday after you write it, okay? All right, so let's see. To approximate the sojourn time Tn, which is the number of visits that the Markov chain makes to some set T on the first n transitions, we have the following result. Don't bother reading the result. I will tell you what it means. So this is the total variation distance. Tn is the true distribution, the true random variable I'm interested in. Tmn is what I will try to compute, where m is me forcing that the largest exponent I will use is little m. Okay? So what I'm saying, the total variation distance between the true random variable and the one that I may be able to compute in my computer is at most the probability of observing a run larger than m. And using the Poisson approximation for run lengths, you can show that that's of order n to the 1 minus c, as long as you select m as c times the log of this quantity, which is where the highest power will concentrate around. Okay. Now, something interesting to see is that if you do 3/2 of the log, this decay probability becomes n to the minus 1/2, which is the rate of convergence of the normal approximation. Okay? So, in principle, if you don't feel comfortable using the normal approximation, you can use 3/2 of that to get a very decent approximation with a warranty error bound. Okay, so now you are not saying, I think the normal approximation applies. You are no longer making claims. You say, I don't want to compromise, but I have now something that I know exactly what the error should be. Okay, now while this is interesting theoretically, it's not very interesting practically, because I'm not telling you how to compute T sub mn. How do you compute the distribution? Okay. And the reason why that seems a bit not so obvious is because there are many ways in which the longest run of m, capital M's, the residual chain, is a most little m. So it seems that I transformed the problem into a new problem where I also need to worry about a combinatorially large number of possibilities. Well, luckily we can overpass that, and here is the result. Roughly speaking, the moment generating function of Tmn, which is what I will use to approximate the distribution of T sub n, can be written as a ratio of two polynomials. Not only that, the error in the approximation can be computed by evaluating that polynomial at 1. So as you are computing the approximation, you are also keeping track of the error. So you are getting the two things together. You are not having a theory for the approximation and a theory for the error separate. They are both coming intertwined. And the question is, how do we compute that polynomial? Well, this polynomial is computed in this way, and I know that's not pleasant to read, so let's move to the next slide. The polynomials T sub mn of the variable z satisfy a linear recursion of order m plus 1. Okay? So that means that to compute that distribution, I will only deal with multiplying polynomials on a recursion of order m plus 1 rather than multiplying polynomial matrices up to an arbitrary order. That's the change in complexity. Okay? All right, so that's for sojourn times, but what about for more complex linear functionals? Yes?
So is there any role that E and N can play there? I mean, if I have freedom in choosing E, right?
You have a freedom to choose E. Well, I will kind of go back to that at the very end, but here's the idea. You want the largest alpha. Why you want the largest alpha? Because the largest alpha, the more often the memory breakers, and the more often the memory breakers, the smaller is the power of m that you need to worry about. And at the end of the talk, I will tell you how to compute the largest alpha. Okay. How are we doing on time? 20 minutes. Okay. All right. So what about an additive functional? Okay. So now we have a total function that depends on the state and the time. Well, we get essentially the same result. The moment generating function of the additive functional is a ratio of two polynomials again. The error is controlled by one of these polynomials evaluated at 1. And this complicated mess, I want to reduce it to this, where for a fixed m, these polynomials satisfy a linear recursion of order m plus 1. Okay? Now the recursion now is not homogeneous anymore. Okay, so terms depend on time, and they must depend on time because the total value depends on time. So there is no way to avoid that. Okay? But if the total function doesn't depend on time, then the recursion is just a m plus first order recursion of polynomials. All right? So here's an example. The only reason why I want to show you this example is because when you publish things on approximation, they always want you to compare your method to something that was already published. Okay? So this was a method published by Erhardsson, who did a compound Poisson approximation of several Markov chains using several lengths from 10 to 1,000. And this is the memory breaker approximation that we produce. And we are reporting here the exact error because the chain is sufficiently small that here we can compute exact errors. And in almost all examples, we got at least one order of magnitude better than the already good compound Poisson approximation. So that's a kind of remove any concerns that we are not losing our minds here. All right. Now, when I draw this, I kind of cheated a bit because originally I wanted a k larger than or equal than 1, and here I assumed that k was 1. So the question is, what do you do when you cannot find k equals 1? Because in the toy example, we were using or assuming that k was 1. And the answer is, well, what you do is slightly more complicated, but broadly speaking, when you cannot use k equals 1, the intuition tells you, well, work with a Markov chain where the matrix is not p, rather p to the k. Okay? However, that doesn't work. There are correlations that you induce there that the memory breaker trick doesn't work. However, we still were able to embed the chain into another chain with a memory breaker with k equals 1. Okay? Now, I don't want to go there because that on itself, it's a talk, but here's kind of the idea. I want you to see just what is the picture we have in mind. Well, if I give you this matrix P, the best alpha you can choose so that P is bounded from below by alpha E will be alpha equals 0. So that means there is no memory breaker. So no trick. The trick fell down to the trash. Okay? But if we write P sub Z and we take the square, we can write P sub C square again as a mixture of two matrices, except that the matrices now are polynomial matrices rather than probability transition matrices. And what is beautiful about this mixture is that a sixth of the time, I will use this matrix with constant rows. So rather than having something that is a measure or a memoryless process, I have a new object that is memoryless from an algebraic point of view. Make sense? A sixth of the time, you use this that doesn't depend on anything. 5/6 of the time, you use something else where there is an influence of what is the I you're looking at and the J you're looking at. So using that, we call this 1/6 the second order probability of the memory breaker. And if you take the third power, you can again write this as a mixture where now here, all the rows of this matrix are identical. However, here, not all the rows are identical. So now this acts algebraically as a memory breaker. And the memory breaker happens 25% of the time. And if you take the fourth power, now it starts to look very ugly, but 5 every 12 times, you will use now this memory breaker. Okay? So in that way, when we cannot use k equals 1, we embed the chain into a different chain where we can use k equals 1. Okay? So these alpha sub 2, alpha sub 3, alpha sub 4 of P, we call them higher order memory breakers because the true alpha is 0, period. There's nothing I can do there. Okay, so let me show you an example. Here's a motif. This has nothing to do with the RNA that is the dopamine motif in C. elegans. We look at 4 genes. Here are the lengths of their promoters from 2000 to 3700. Here is the number of matches with the dopamine motif. And in this particular application, people are worried about, is this number of matches significant or not? So they're interested in computing a p-value. Okay? So to compute a p-value, we wanted to know, well, what's the probability of observing the dopamine motif 7 times in the promoter of this gene that has length 1900 or 3600. Now, to solve this problem, we needed to work with a Markov chain with 1400 states roughly. So now you see the 3 states on the toy problem now became 1400 states. And we needed roughly 3700 transitions. So if you do this by brute force, what's the probability to observe the motif 7 times in 3700 transitions? I will have to take a large power of a Markov chain with 14,000 states. Okay? And we were never able to compute that in any reasonable amount of time. So we decided to go for our approximations. Now, for all of these chains, there were no memory breakers, but there were higher order memory breakers. And to discover the higher order memory breakers, I'm telling you the k that I had to consider. The largest was 45, the smallest was 11. So we took the 45th power of P sub C to identify a memory breaker. And once we have a memory breaker, the whole problem goes from linear scale to log scale. And that's what we did. And we obtained these p-values that range between 43% and 79% with all errors that are of order 10 to the minus 3. So all the p-values, you can trust that you get the right values. Now, why I'm telling you that? Because many times when you compute approximate p-values using the normal approximation or the compound Poisson approximation and use the theoretical bounds, the error bounds are usually so much larger than the p-value that you say, oh, my p-value is 10 to the minus 50 plus minus 10 to the minus 4. So it's like you did nothing. So that's why one wants methods that are sometimes non-asymptotic, so that hopefully the error is not going to be so pessimistic. Okay. All right, so finale, this is related to your question. Mr. Doeblin, he introduced this idea in the literature to find from below this matrix alpha E. And this is the optimal alpha. He said the optimal alpha consists in the following. On every column of P, take the minimum, and now add up all those minimums. That's the optimal alpha. The largest alpha, the one that will bring memory breakers more often. Now, the problem is that if every column of P has a 0, the memory breaker is 0, so everything falls down to pieces. And that's why we were looking at the higher order memory breaker. Okay. Now, in 1937, in a report, Doeblin said, in a finite state space, the following are equivalent. Well, the sequence PK is weakly ergodic, which means that, well, so this is a non-homogeneous Markov chain theory, okay? Weak ergodicity. And what it says is that no matter what happens, you eventually lose memory of where you started. But weakly ergodic doesn't mean that you converge to a limit. It means that no matter where you start, everything starts to oscillate close enough so that asymptotically you cannot tell anything apart. That's the weakly ergodic part. And what he said is that to have a weakly ergodic sequence of non-homogeneous stochastic matrices is equivalent to be able to parse the matrices into groups so that his coefficient of each group, if you add up all the groups, diverges. That's what he said. But Doeblin died before he proved this. So the first proof due to this was on the 70s by Eugene Seneta, a probabilist interested in non-negative operators. And his proof was kind of weird. It was weird in the following way, that he used ergodicity coefficients that were defined after Doeblin's time to prove Doeblin's result. So in that sense, it's probably not the proof that Doeblin had in mind. Okay. So why I'm telling you this is because we started to solve a very practical problem, and suddenly we were looking at very theoretical probabilistic statements that you are concerned about. And then you start to wonder, is there a connection here? Well, this is what happens. One can show that the optimal memory breaker is the largest alpha for which there exists a measure E such that P is greater or equal than alpha E. That's the best you can do. But when we realized that that's the optimal alpha, and then we realized that Doeblin had defined it also in this way, we were able to show several properties about Doeblin's coefficient that were not known before. And one of the properties that it was not known before was that it's sub-multiplicative, meaning that 1 minus Doeblin coefficient of PQ is less or equal than 1 minus Doeblin coefficient of P times 1 minus Doeblin coefficient of Q. That was not known. And the reason why we were interested in that is because we wanted to say that, study the complexity of our algorithm. And if we had sub-multiplicativity, we had a better grasp at the complexity than if we didn't. Okay? So we realized this, but then talking with Seneta, we realized that now we could prove Doeblin's coefficient in 2 lines. That's an exaggeration, but very fast, just using Doeblin's definition. Okay, so we suspect that Doeblin knew his coefficient was sub-multiplicative, We suspect that. And now this is a corollary of this very practical application, which is in finite state spaces, alpha, which is defined by this in our approach, but by Doebling's, leads to a novel but elementary proof of Doebling's characterization of weak ergodicity. And why I'm showing you that is because I always like to see theory coming out of things, but this is a perfect example where you are chasing a very practical problem, very real world problem, and suddenly you end up doing mathematics, totally out of the blue. Okay? And I thought that was something I couldn't not tell or share, especially with the younger people in the audience. So that being said, this was partially funded by my NSF grant. And if you want to see the proof of Doebling's characterization using this more straight to the point method, here is a conference proceedings. And if you want to see the full article with all the details that I was discussing today, you can see at this publication on the Journal of Math Bio. Thank you.